We all think we know what temperature is, right? It's just how hot or cold something is. But what if you're trying to measure the temperature of something, well, a little more exotic? Imagine plasma. That's the fourth state of matter. And just to make things interesting, it's packed with microscopic dust. How on earth do you take the temperature of that? Today, we're going to explore a wild new technique that measures temperature not by how fast particles are moving, but simply by where they're sitting.
All right, so here's our game plan. First, we'll dive into the strange world of dusty plasma. Then, we're going to put the old way of taking temperature head-to-head with this new method. We'll see how scientists tested this new idea in a computer simulation before trying it out in a real lab. And finally, we'll wrap up with why this could be a real game changer for physics.
Okay, first up, let's get our heads around this environment we're talking about. A plasma that's literally full of dust.
You know, it sounds like a simple enough question. What happens when you just sprinkle a little dust into plasma? But it turns out adding these tiny grains creates a physical system that is anything but simple. Something really extraordinary happens.
So these little dust particles basically act like sponges for electrons. They just soak up all the free electrons floating around in the plasma, and in the process, they get this huge negative charge. Suddenly, they're not just passive specks of dust anymore. Oh no, they become major players that are interacting with each other through some really intense electrical forces.
And that right there brings us to the core problem. At its heart, temperature is all about kinetic energy. It's a measure of how much the particles are wiggling and moving around. But in a system like this, where everything is so strongly connected by these powerful forces, trying to get a clean measurement of that individual movement is incredibly tricky.
This whole challenge really sets the stage for a showdown between two different ways of measuring a dusty plasma's temperature. You've got the classic method, which is all about speed, and this clever new one, which is all about spacing.
So let's break this down. The old way, kinetic temperature, is kind of like trying to understand the energy of a huge traffic jam by standing on an overpass with a radar gun and clocking the speed of every single car. I mean, it works, but it's a ton of work and you need a lot of data. The new way, configurational temperature, is totally different. It's like flying a drone over that same traffic jam and just taking one single high-resolution photo. By looking at the spacing between the cars, their configuration, and understanding the forces between them, you can calculate the entire system's energy without knowing how fast a single car is going. It's all about position, not motion.
Now, before you take a radical new idea into a real, expensive lab, you want to test it somewhere you have total control. And that place is a computer simulation. So that's what the researchers did. They built a virtual dusty plasma to see if their snapshot method for temperature actually held up. And they didn't just run one test. They ran two different kinds of simulations. First, they used a molecular dynamics simulation. This is like a super-powered physics engine that calculates the exact motion of every single particle over time. It was perfect for comparing the old kinetic temperature directly with their new configurational one. Then, they used a Monte Carlo simulation. This one is a bit different. It makes random changes to the system and just checks if the new setup is stable. This was the perfect way to see how quickly their new method could react to sudden changes in temperature.
And honestly, the results from that first test were just, wow, they were impressive. This table kind of simplifies what they found. That gamma value is just a fancy way of talking about how orderly the system is. A high gamma means a low temperature, so things are more structured. And as you can see, across a whole range of conditions, the configurational method, the one that only uses position, absolutely nailed it. The temperature reading was a near-perfect match every time.
This quote really sums up the second test. The researchers put their virtual plasma through these things called quenches, which are basically just sudden, really extreme changes in temperature. And the configurational method, it kept up perfectly. It tracked those crazy changes instantly and accurately. So the simulations were a huge success. The method was both accurate and super responsive. Okay, so it worked like a charm in the clean, perfect world of a computer, but now for the real moment of truth. It was time to go to the lab and see how this new idea would handle the messy, unpredictable reality of a physical experiment.
So the test was done in a machine called the Dusty Plasma Experimental Device, or DPAX for short. Inside, they created a real dusty plasma where the particles were interacting so strongly that they actually locked themselves into a solid crystal structure. It's pretty amazing. Then, just by lowering the gas pressure, they could melt that crystal and turn it into a messy, fluid-like state. This was brilliant because it gave them two totally different conditions to test their method on. In that first state, at high pressure where the dust formed a beautiful, perfect crystal, the results were fantastic. Just look at the chart.
The temperatures from the old method and the new one were practically identical. It was a perfect confirmation. Just like in the simulation, the theory worked perfectly in a nice, ordered system.
But then, they lowered the pressure. The crystal melted into a chaotic fluid, and something completely unexpected happened. The two methods suddenly gave wildly different answers. The configurational temperature reading was almost 4 times higher than the kinetic temperature. That's not a small error. That's a huge deviation.
So what gives? What went wrong? Well, this is the crucial part. It wasn't a failure of the method itself, but a limitation of the model they were using to crunch the numbers. Remember, for the whole snapshot idea to work, you need to tell the computer exactly what the forces are between the particles. And in that messy, chaotic fluid state, the simple model they were using just wasn't accurate enough anymore. So the big lesson here is that this new tool is only as good as the physics you feed into it.
So, let's put this all together. What's the final takeaway? What does this new tool actually mean for the world of physics?
Even with those limitations, this configurational temperature idea is a really big deal. It gives scientists a way to measure temperature in systems where tracking every particle's speed is just impossible. It's especially huge for analyzing simulations like the Monte Carlo method, which don't even have velocity data to begin with. And you know what? Even the part where it failed in the fluid state is incredibly valuable because it shines a giant spotlight on where our physical models need to get better. It's not just a new ruler, it's a tool that helps us understand physics itself.
This whole project was focused on dusty plasmas, sure, but the core idea has implications that are so much broader. It's a fundamentally new way to think about the energy of a system, so it leaves you wondering, what else could we learn about the universe if we could figure out its energy not from the chaos of motion, but from the simple, elegant pattern of its structure?